Greetings, math fans. All right, so this is day 6, and we're going to talk about two different topics here. The first topic is actually just an example. This is to kind of help you with a homework problem, and it's really talking about continuity and differentiability. All right, so let's just start out with a nice little friendly example here. I want you guys to find the values of A and B such that f of x will be continuous and differentiable at x equals 1. Okay? And here's your function. F of x is equal to negative 2x minus 1, where x is greater than or equal to 1, and ax squared plus bx, where x is less than 1. Okay? So the first thing I want to do is we're going to deal with continuity, where it's continuous. Okay, so let's talk about that. Continuous. Remember, limit as x approaches 1 from the positive side has got to be equal to the limit as x approaches 1 from the negative side, which is equal to f of 1. Right? That has to be true. So the way you check to see if that's true, right? Obviously, we're looking at both functions here, right? And our critical value, of course, being 1, is we're just going to plug in 1. So we're going to plug in 1 into, or for x equal to 1, right? Of course, plug x equal to 1 into both equations and set them equal. Okay, pretty easy. So we're going to have negative 2 times 1 minus 1 is equal to a times 1 squared plus b times 1. And so we get negative 2 minus 1 is negative 3 equals a plus b. Okay, so we've got one equation here. Well, what is this going to turn into, math fans? Of course, you probably should recognize it's going to turn into systems of equations, right? Because I have one equation for continuity, and I'm going to create another equation for differentiability. And so remember, when I'm looking for differentiability, I'm looking for the slope of the tangent line. I'm looking for the slope at 1 of each of those functions. And what has to be true about that? Well, let's do that. So I'm just going to cursor down here a little bit. Okay, so this is one of my equations. Just we're going to keep that one there, and we're going to look for differentiability. And remember, the limit as h approaches 0 from the negative side has got to equal the limit as h approaches 0 from the positive side. Okay, so let's go from the negative side first, and that's going to be your ax squared plus bx, right? X is less than 1. So we're going to say limit as x approaches, or h approaches 0 from the negative side of a, and then of course it's 1, so it's 1 plus h squared plus b times 1 plus h. All right, minus, and that in parentheses, a, and then it's 1 squared plus b times 1. Okay, and that's all over h. Okay, so we have limit. Let's keep going here. Again, you got to show your work here, math fans. Remember, I'm always pushing for AP exam. Okay, they want to see work. So we're going to get a plus 2ah plus ah squared plus b plus bh minus a and then minus b all over h. So we can simplify that. Limit as h approaches 0 from the negative side. The a's cancel, the b's cancel, and we have we can factor out now an h, right? That's our goal here because we need to cancel with that denominator. So we have h times 2a plus ah plus b all over h. That cancels, and then I can do direct substitution, and I get 2a plus b. So that's the one-sided limit, and now we got to find the other side limit. Well, before we actually do that, I want you guys just to notice. So let's do limit as h approaches 0 from the positive side of negative 2x minus 1. Of course, we can do that. We can do the limit, but I'm going to take a little shortcut. Really, you can't do that if you're doing when you're doing your AP exam and you're having to show all your work for the free response. But what is the slope of this tangent line? Well, isn't the slope of that whole line negative 2? So any tangent on there is also the slope is negative 2. So my slope is negative 2 for that guy. And this is our slope here. So what do? I set those guys equal to each other. So I have 2a plus b equals negative 2. Okay. And now I'm going to use this equation right here that I created. A plus b is equal to negative 3. And then it's just systems of equations, and I solve for it. All right, so let's multiply this guy by negative 1. So we get 2a plus b equals negative 2. And negative a minus b equals 3. The b's cancel, and we get a is equal to 1. All right, and then let's plug it back into plug it back into this equation here. So it's 1 plus b equals negative 3. Subtract 1, b is equal to negative 4. Okay, so that's our answer here. A is 1, b is negative 4. And that makes it continuous, and it makes it differentiable at 1. All right, real quickly, our graph for this function, kind of plugging things in. Let's move things down here a little bit again. I just want to sketch it very quickly. It's meeting at positive 1, and it's continuous there. And so this value is going to be 1, negative 3. Okay, and the equation, of course, the slope, when it's greater than 1, the slope is negative 2, so it's down 2 over 1, like that. And so that's that function. That's the linear function. And the other one's a quadratic, and that's going to look like, I'm going to try and make it a good graph here with that. It's going to look like this. Okay, that's kind of what your graph looks like. All right, sweet. All right, so let's talk about our main topic here. And our main topic is called local linearity. And basically, local linearity is a function that is differentiable resembles its own tangent line. So this is the deal, math fans. You need to zoom in. So you need to zoom into the function to investigate local linearity. My example, just to kind of start off here, y equals x squared. Okay, and now I want to ask you guys: is y equals x squared, is that differentiable at every spot on that graph? Yes, actually it is. Okay, but really what I do is I want to talk about it. If I graph y equals x squared, okay, that actually hits it right there. Okay, and let's just, for the heck of it, let's look at this spot right here. Okay, and if I zoom in, what's going to happen is you're going to see a graph like this, and you're going to zoom in even more. It's going to look like this, and eventually it's going to be a straight line. Okay, so this is actually going to be a straight line. And then if it's a straight line, that's why they call it locally linear, because it is a straight line. Okay, and that's what I mean by local linearity. Now, as opposed to this, let's clear this here. And if I give you y is equal to the absolute value of x, okay, if I graph this, it's going to look like this, right? And if I zoom in on this spot here, if I keep zooming in, what's going to happen? I'm still going to have, no matter what, I'm always going to see a corner, right, which is the absolute value. So this is never locally linear. Okay, never locally linear. And we're going to actually use our graphing calculator in a little bit to kind of look at that. But basically, I want to say here is differentiability. If it is differentiable, differentiability, and this means implies. If it's differentiable, that implies continuity. Of course, right? If it's differential, it's got to already be continuous. That's the first thing you check. Okay, and also differentiability implies local linearity. Okay, it's got to be locally linear there. It can't have a corner or a cusp or vertical tangent. It's got to be locally linear. And speaking of vertical tangents, a vertical tangent is not a local linearity. It's not linear. Okay, so like when you have y is equal to x to the 1/3 power, and you have something like this, oops, like this. Okay, sorry, it's kind of messy. Okay, that, and if I zoom in on that spot right there, it's going to show me a vertical line, but that is not locally linear there because this is an undefined slope, or it's right. It doesn't have or it's a vertical tangent, so there's really no slope at that location. So just make sure you're clear about that. Okay, that's not locally linear there. All right, so let's use our TI a little bit now to investigate some things here. So we're gonna use our TI 84 to investigate. And we're going to look at f of x equals absolute value of x. Okay, so of course you're going to type in f of x, or it's going to be really, right, y is equal to abs x. And then what we're going to do is we're going to zoom in. So let's just bring up the TI here. Okay. So y equals, go under math, under number, absolute value of x. Okay, and you start out, it's always good to start out with zoom 6 right there. Okay, it gives us a nice graph here. And what I want to do is, again, to investigate local linearity, I'm going to zoom in. I'm going to zoom in on that one spot there, of course, the spot that I'm concerned about, which is really at the origin for this one. Okay, so I'm going to hit zoom 2, hit enter, and you can just keep hitting enter, and it zooms in more and more and more. And you're like, well, wait a second, Mr. Crow, is it really zooming in? I can't. It doesn't seem to be changing. Well, actually, it is zooming in more, but the deal is, it is not locally linear. Not locally linear. Okay? And that's just by investigating it, by looking at that. Does that make sense, everybody? I hope. Okay? And that's, again, looking at that one spot there. All right, let's actually put a different function in. Let's put in f of x is equal to x minus 1 squared plus 2. Let's look at that. So we're going to go back to our TI and clear this out of here, and we're going to say parentheses x minus 1 squared plus 2. Okay, and then math fans, you need to reset your zoom. So if you just hit graph right now, it's not going to give you very good. In fact, it might not even be in there in the window. You need to go zoom, and if you do zoom 6, that actually puts it back as a standard graph. All right, and so here's our graph. And what I want to do is I want to investigate what's going on at x equals 1, right? Isn't that's kind of our main point, right? We're saying x minus 1 equals 0, so x equals 1. That's our basically our vertex, right? So let's investigate at x equals 1. Okay, so I'm going to do, now I want to be to make that my center point that I'm investigating. So if I do zoom in, I mean that's okay, but what's going to happen is really I'm zooming in on the origin here. If I do, right, I just want to show you, zoom in, hit enter. See how it's kind of over in that corner over there? What I want to do is I would actually want to set my window manually. And I know that let's look at my vertex for this problem is going to be 1, 2. So let's set my window, my x window is going to be between, let's just kind of put it in the middle. How about between 0 and 2? And my y window, let's put that between 1 and 3. That just gives us a good view. So then when we zoom in, that'll be like right in our center area. So let's do that. My window is going to be between 0 and 2. Okay, and the y min is going to be 1 and 3. That's going to give us a nice graph. And we go to graph it. Ah, look at that. Beautiful. There's our vertex. Okay, so what I want to do is now I can zoom in. When I hit zoom in, so zoom 2, and hit enter. Okay, it's keeping my vertex right in there. But look what's going on, math fans. Look at this. I'm zooming in on this parabola. Watch. Let's keep going. Oh, look at that. Oh man, it's a straight line. Okay, this happens to be a horizontal line because I'm looking right at the vertex. But that's the deal. Is I'm looking at it and I'm zooming in more and more and more. And this is locally linear here. So it's locally linear. Okay, and I can look at any spot on there because that is it's a differentiable function, but it's locally linear at that spot. Okay, so that's kind of cool. Let's do another function here on the TI, and let's do y is equal to the cubed root of x minus 1 plus 2. Okay, so really you got your same critical point here. Do you guys agree that we're going to deal with 1, 2, right? So actually I can use my same window. My x window is going to be between 0 and 2, and my y window is going to be between 1 and 3. All right, so let's bring up our TI again here, and we're going to do y equals, and this is going to be instead of, it's going to be x minus 1 raised to the 1/3 power. And you could use there's another feature there, the cube root. You could use that too, but I'm going to use this. Raised to the 1/3 power, close parentheses, and then plus 2. Okay, I'm going to do zoom 6 first just to get our standard look. Ah, very interesting. Look at that. Remember that? If it's the cube root of something, you're going to have a vertical tangent. And there it is. Okay, but let's investigate a little bit what's going on at that vertical tangent. So I'm going to set my window between 0 and 2 for x, and between 1 and 3 for y. And let's graph. Ah, look at that. There's our vertical tangent. Okay, so let's keep investigating that. So if we do zoom in, so zoom 2, hit enter. Okay, hit enter again, hit enter again. Now look at that. Okay, that's just showing it's a vertical tangent. But please don't don't look at that and go, oh hey, it's locally linear. That's a vertical tangent. It's not locally linear there because again, that slope, you can't have an undefined slope. Okay, that's just checking to see that it's a vertical tangent. So in this case here, it's got a vertical tangent, which means it's not locally linear. Okay, because it's undefined. The slope is undefined at x equals 1. Okay, so that means it is not differentiable at x equals 1. That's really what you're trying to tell me here. Okay, as opposed to the other function that I did. It was differentiable. The absolute value, not differentiable at x equals 0. That was our first function we did. Okay? And of course, you give me the reasons, right? This is because it's a vertical tangent. The absolute value one was because of a corner. Okay, that makes sense, right? And let's do our last example here. Y equals the cubed root of x minus 1 squared plus 2. Okay, now what's that going to be? Again, remember, if we do an informal reason for why it's differentiable or not differentiable, and this is not differentiable because of, hopefully you remember that, because of a cusp. All right, remember that's like saying y is equal to x to the 2/3 power. That's going to give us a cusp because of that square there. It makes it positive all the time. But let's actually investigate this a little bit. Okay, so I'm going to do y equals, and I'm just going to change, the only thing I need to change here, math fans, is I need to change this to the 2/3 power. So that's it. Okay, and I'm going to do zoom 6. Ah, look at that, nice cusp. Beautiful. All right, and then again, let's set our window because it's kind of, again, our critical value is going to be at 1, 2. So again, our x window is going to be between 0 and 2, and our y window is going to be between 1 and 3. It's going to give us a good window. So let's do that. Window between 0 and 2, and y is between 1 and 3. And we graph it, and look at that. Okay, cool. So let's zoom in, zoom 2, and hit enter again a couple times, enter a couple times, couple more times. Okay, so you see what's going on. You're still getting a cusp no matter what. So that's my investigation. We're still getting a cusp. So that's why it is not differentiable at x equals 1 because of a cusp. And it is, of course, it is not locally linear. All right? Okay, so again, locally linear is it's investigating it, and if it's not locally linear, it's not differentiable. Okay? That's really, really important concept. All right, it's pretty reasonable. All right, let's talk a little bit more about the graphing calculator. We've just like graphed them and investigated them. Okay, but let's actually talk a little bit about one of the features of your graphing calculator, and this is called n deriv on your TI-84. Okay, n deriv. And basically what it is it's going to allow you to take the derivative at a point. Okay, it's not going to let you get an actual function, but it's going to let you take the derivative at a point. So let's just start out with a function here, y equals x squared. And let's do dy dx. Let's just do it by hand because I want to show you that and have you be all amazed. Okay, if I do limit as h approaches 0 of x plus h squared minus x squared over h, that gives me limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. The x squareds cancel, and we have limit as h approaches 0. I can factor out an h, so I get h times 2x plus h all over h. That cancels, and I do direct substitution, and I get 2x. So that is dy dx. Okay, and now if I said find the slope of the tangent, so let's say I do find f prime of 3. Well, slope of the tangent at 3, well, that's saying 2 times 3, which is 6. Okay, so we did a little bit of work, and we found the slope of the tangent at 3 is equal to 6. But let's use our calculator now. This is very exciting. So try to remain calm here, math fans. Let's go to let's quit out of here. Okay, and we're going to use you go under math, and it's number 8, which you can just type in 8, or you can cursor to 8. Okay, but it's n deriv, n deriv. And we have three parameters. So here, let me write this out before I type it in the calculator. Okay, so it's n deriv, and the three parameters are, well, first of all, we're going to put the function in. So it's going to be x squared, and then x, comma, and our value that we're putting in there, which is going to be 3. So again, the first parameter is our function. The second parameter is we're taking it with respect to x, so that is our variable. So it's our variable, and this is with respect to x. Okay, and 3 is the, let me put this down here. The 3 is the actual location. So that's the x equals 3. That's our value at 3. Okay, and what should that give us? It should give us 6. Let's see. I'm not quite sure if that's really going to work or not. Well, I hope it works. Okay, so we're going to put x squared. So x squared is our function, comma. Make sure you put a comma in here, which is right above your 7, comma x, comma, and then 3 is the value we're putting in there, and we enter, and voila, we have 6. Sweet. So 6 is our answer. Okay, so that gives, I can put whatever function I want in there. I take the derivative and I use the graphing calculator to figure out the derivative at that point. Now the deal is, when would you use this? Well, obviously, if it's a free response, that is not an acceptable method. If they say, "Ooh, show show the slope of the tangent at 3." Okay, and if you write on there, well, I used my graphing calculator and used n deriv, okay, that's going to give you like 0 credit. So you can't use it for that. But of course, if it's multiple choice and they say, here's this big old nasty function, find the slope of the tangent at that point. If you spend an hour, well, you won't be spending an hour, but if you spend 10 minutes trying to derive it, as opposed to going, I can use my graphing calculator and I can actually put it in the graphing calculator with n deriv and get the value, that's what you're going to want to do, math fans. All right? So just kind of keep that in mind. Let's talk about when the TI can't handle a derivative. Okay, so this is kind of important here. Your TI can't handle n deriv when it's not differentiable. Okay, and that makes, what's going on here, math fans, is the TI is, let's explain. I want to explain here a little bit, just with the graph. Okay, your TI is actually looking at, if I'm trying to find the derivative at this point, it's actually taking points on either side and it's shrinking this down. So it's shrinking that down, shrinking it down, shrinking it down, shrinking it down, shrinking. So it's turning that secant, or the secant line into the tangent line. Kind of what we did back in the day when I first explained to find the derivative. Okay, I closed the gap. Well, what it's doing is taking 2 points, one on either side. I didn't do that. I actually just took 1 point and I said it's getting closer. That secant line is turning into a tangent line, but it's taking points on either side. Okay, and shrinking it down. So it doesn't know, if something's not differentiable, it doesn't know that. It's taking, no matter what, it's taking it. And here's an example, and this is what I'll show you guys in a second. If you have absolute value and I say, hey, find the derivative at that point, it's going to give you value because it's going, oh, let's take these points and let's shrink it down, shrink it down, shrink it down, shrink it down. So it's going to give you a value, but it's going to be wrong. So you can't just rely on your graphing calculator to be giving you the right derivative if there is not a derivative in the first place. Okay, it's going to think there is one. So you have to know right away that there's not a derivative here because, gee, there's a vertical tangent, or gee, there's a corner, or gee, there's a cusp. Okay, so you have to know that, and the calculator doesn't know that. So let me just kind of give you an example. If I did n deriv, let's do the absolute value, n deriv of absolute value of x, that's your function, comma, x, comma, 0, right? There is no derivative here. You guys agree that it's a corner? Okay, but watch. If we use our graphing calculator, it is not that smart. So we're going to do math and 8 and deriv, and we're going to do math, go over to number, and do absolute value of x, comma, variable x, of course, comma, 0. Watch what's going to give you. It should like not give it to you, right? But voila, it's giving you 0. Boo, 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 boo. Okay, it's not 0. So you guys need to know that it is not 0, not 0. But that's what your calculator is giving you. So again, just kind of know your calculator. All right. All right. Last thing I really want to show you guys is how do you graph a derivative function. That's actually pretty easy. Let's go back into here. Let's clear this, and we're going to do y equals, and let's do y equals x squared. Okay, we just did that one before. Didn't we say it's if you have f of x equals x squared, our derivative f prime of x is equal to 2x. Right? So let's see if the graphing calculator is going to work. I keep saying let's see if it's going to work. Of course we know it's going to work, but it's always kind of exciting to check some things out here. So I'm going to do the first y1 is equal to x squared. And this one's going to be math, okay, 8 and deriv. Now this is the deal. I can write x squared again, and that's really not that difficult. Or I can just say y1. And sometimes when you have a big nasty function, why do you want to type that whole function in again and maybe make a mistake? Why not just say, hey, I'm taking the derivative of y1. And that's what you do. You vars, which is right next to your clear key, vars, go to y vars, hit enter, and hit enter, right? So now you actually have y1, which automatically plugs in that x squared into there. Okay, so that's your function, comma, x, comma. Now, we usually put a value in there because I want to say, hey, what's the derivative at 1, 2, 3? But it's going to be at any x value, so you're going to put an x in there. And you're going to close that. All right, and now we're going to do zoom 6. All right, and there we go. Kind of did it fast for me. Here's your parabola, y equals x squared, and of course the derivative is 2x, and there's your 2x. Okay, so that's kind of nice for graphing the derivative function. All right, let's look at one more function. If I do y equals absolute value of x, so let's go math, absolute value, which is number, absolute value of x. Okay, and then I do zoom 6, and there it is. Huh? Check that out, man. You can see what's going on is the derivative is -1. I mean, let's look at the equation, right? If I broke it up into a piecewise function, if I broke f of x equals absolute value of x into a piecewise function, wouldn't it be f of x is equal to negative x when x is less than or equal to 0, and positive x when x is greater than 0. And then sure enough, that's exactly what it did here when it graphed it. You can see here it's negative x here for the left hand side, and for the right hand side it's positive. So look at the slopes. I mean, just looking at the slope of these equations, isn't the slope when it's less than 0 -1? Well, there it is. Okay, and then what it does, you have your little jump over here up to +1. As soon as you hit 0, it jumps to a positive slope. All right, so that's why it is not differentiable at that value. All right, because the slopes jump, right? In fact, if you look at the slope graph, it's really a jump discontinuity, isn't it? Okay, non-removable discontinuity. All right, so that's it, math fans. I just want to show you learned a little bit about with the graphing calculator, and also about local linearity, and we did that one example at the beginning, but I hope you learned a little bit about all of this. All right, adios, math fans. Have a great day. Bye-bye.